Okay, so chapter 17, part 1. We are now at the point in our statistics class where we start looking at distributions that have an added feature or a different feature than before. And actually for the remainder of this semester, we will be talking about sampling distributions. We will be using sampling distributions. So before we journey into the new stuff, into the idea of what is a sampling distribution, let's remember what we've been familiar with in the past and what hopefully you're feeling pretty good about. Up until now, we have looked at distributions. One of the ways of looking at a distribution of data was to use a histogram. We know there were other graphs, you could use tables, etc., etc. Okay, so distribution is not just limited to this one particular visual. However, this is a pretty nice one for the discussion today, okay? So a histogram, those bars you see that are connected with no spacing, that was one way that we could look at the balance of our data to understand how things were relating to each other, how data values were relating to each other. And remember from the past, if you had created a standard histogram, like I've got up under that smooth curve there, you would have been counting. This would be representing the counts of individual values or values from individuals, okay? For example, if we were looking at a graph of the height of women, okay? Every single time there's an occurrence, right? The height of this bar, the frequency, or even relative frequency, if I had made this into terms of percent, this right here would be referring to the number of women that were whatever this height was. Maybe it's 60 inches. Okay? So it used to be, up until now, that we were looking at what is the probability of an individual being this height. And we were asking questions like, what is the probability of a or an individual, singular? Because again, these pictures were individual values. This is very important, okay? This is an important transition. And we know that these histograms that we were creating, we hopefully had used good sampling techniques. And we hopefully had representative samples that had distributions that were similar to the parent distribution. And remember, that's why we actually stepped away. We were, making some of these assumptions, and that's why we would step away from the very, very detail-oriented histogram, and we stepped out to more of a macro level, and started looking at just that smooth curve. And we would say, hey, I saw about this shape from my sample, so now let me discuss the behavior I'm expecting for all women. Still individuals, but for all women. So starting again at that micro level, that smaller level of a histogram, looking at the balance of the data. Maybe we use QQ plots, other things, not just histograms. But once we saw the type of shape, if it qualified as normal, for example, we would remove the values and we would talk about the shape. And we would talk about the features of the shape. And we would say, given characteristics like this right here being the average and this being the standard deviation, can I now understand the behavior of these individual women's heights or these individual values? And this was pretty nice. Remember, though, that this conversation started with me saying that we first had to look at the histogram and that we wanted to have a histogram or whatever distribution visual we were looking at. We wanted this to be representative, matching the truth of the parent population. Right? So if I were looking at something, for example, like people's activity on social media for some given post, I may actually end up having this type of shape, right? I may have something where in the beginning, if time is on the x-axis, I may have something where in the beginning there's a lot of time spent on this post. And then as time progresses, there's less and less time spent on whatever the social media post is. right? So if I were looking at someone's usage time, and I was saying, okay, well, what am I going to expect? This person right here on their post, they spent this much time, right? Or later on, people were spending a different amount of time. It would be individual. And with it being individual and representing the truth of that parent population, we were not guaranteed that everything would be normal. For example, human behavior on social media would not be a normal distribution. But you know, a lot of this class we've spent time talking about the importance of a normal distribution. We've talked about things like, well, the empirical rule, if my distribution is normally distributed, I can already start to approximate percentages, areas under those curves. I can start to make some inferences about my data on kind of a smaller scale, but I can do that if I have a normal distribution. So we actually start to look at distributions from a different angle. We start to look and say, let me make this zoom out a little. We start to look and say, you know, instead of individual values, let's consider for ourselves groups of data, grouped up values. When we use the terminology sampling distribution, we are talking about taking an entire sample and getting some descriptive measure off of that entire sample. Sampling distribution, looking no longer at individuals, but looking at groups in samples. And so what I mean by group values would be, if I were talking about the height of women, I might say something like, okay, instead of looking at individual heights, what about, I guess the descriptive feature, the sample statistic that I might be interested in, using that to predict some population parameter. If I'm looking at height, I guess average would make sense, right? That's a feature I could easily summarize off of the values, and it might have some meaning to me. So on my graph, I may, instead of looking at individual values, I may say, you know what, let's talk about average. What are the averages for each group or each sample I've collected? So you might see something, for example, where we say, hey, look, over here I have an average for this entire group of women, whatever the sample size might be. For this entire group, I have an average of 58 inches, right? And then you might say, okay, well, here's another group. And this group of women, their average, their X bar, that was 60 inches. And we still end up, when using averages, we still end up with a similar mentality with a histogram of looking at frequency or relative frequency, where the height of these bars is now representing the number of times that average would have occurred. And that's very different. It's actually quite, it's a quite powerful angle to begin taking. And a lot of it's theoretical. You know, maybe we're not going to actually take this many separate averages, this many different groups of sample size, I don't know, maybe sample size 50. Right? Oh, look, I had a group of 50, and 58 was the average for that group, and 60, well, that group of 50 was a 60 for the average, and the other group was a 60 for the average, and the other group was a 60 for the average. So literally, in theory, we have all of these small groups that we're thinking about, and we're saying, well, hey, what was the average? Let's talk about the feature. What was the average on this group? What was the average on this other group, And we take those averages and start to graph up how often it happened. So what I want you to do for a second is I want you to ask yourself a question. Would it be more common, let's pretend that 60 inches was the mean up here on individual values, and it was the mean down here on averaged values, averages for the group, for the sample. It's the most popular place, right? We're going to say not just was it the mean, but in both cases we're going to just let it be normally distributed for visual purposes, okay? Would it be more unheard of to have a woman who is 50 inches tall, not even having to care that much about the standard deviation, just thinking conceptually for a moment? Do you think it would be more possible or more reasonable to have someone, an individual, 50 inches tall? Or would it be more reasonable or versus more unheard of to have an entire average for a group at 50 inches? Which one would be more rare? Which one would be more acceptable? Here's another thing I want you to think about. Let's think about test scores. If I told you all, hey, on test 1, let me get another sheet. This is concept here. On test 1, I took averages from different classes. I'm going to use my classes as different samples, okay? So I'm going to say, okay, well, looking here at group or sample 1, I had individual scores, individual scores. I had a 30, I had an 80, I had an 85, I had a 99, whatever we had for those scores, right? Would this value be kind of reasonably possible when looking at individual test scores versus when I'm looking at the average for the entire group or each entire sample? So there's group 1, here's group 2, right? And they have some scores, 70, 80, 100, whatever they've got going on, right? Different scores. Would it be more plausible to say that I would expect to have maybe one person who just absolutely didn't study, right? That individual score that's that low. Or would it be more plausible to say, okay, the average for the entire group 1. Class 1, their average for the entire class was a 30. Right? Assuming that the whole class didn't actually fail. I want you to think about how much more difficult is it to move an entire average back and forth for an entire group of maybe 30 students compared to one individual having a bad day. And hopefully in your mind you're saying, this would be more rare. This over here, this average moving, is going to move it's going to be more difficult to move compared to an individual value. Now, yes, we do know that average of all of our measures of center, average is one that can jump around a little more with outliers, right? So we do say, you know what, it is acceptable that I'm going to get some kind of a behavior that's not always exactly on the truth. It's not always exactly 60 if that's the true height of women. That average would not always be exactly 60. It's still going to bounce around a bit. But what I want you to consider is that it's much easier to bounce back and forth with individual values. One person is short, one person is tall, right? That's more plausible than for me to jump around a lot with an entire group of, say, 50, or with the test example, an entire group of, say, 30. It becomes more difficult because you see one person making a 30 while everyone else had an 80 or better. It might move the average down a bit, but it's certainly not going to swing it all the way to 30. It takes a lot more change, a lot of different individual scores to pull that average down to a whole 30 for everyone. Or to pull the female height, the average down to a 30 for everyone. Averages are much more consistent than individual values. when we begin looking at them on a distribution. So you see, sampling distributions are quite powerful. Because no matter what it is that we're looking at, no matter what sample statistic we're choosing to talk about in theory on our graph, whether it is averages or whether it is p-hat proportions, we've looked at the percent for an entire group, no matter what it is we're looking at, we begin to see that the consistency is such that things will pile up right in the middle close to the truth. And the consistency is such that if our sample size is sufficiently large, no matter what the original shape was, whether it was this right skewed shape or it was originally this bell shape with individuals, whenever my sample is sufficiently large, I will end up with grouped values that become normally distributed when I'm talking about sampling distributions. We like normal distributions. We like the fact that we're expecting more consistency. We're expecting things to really pile up closer together when I'm talking about an average, no matter what the average was. If I'm looking at time here, there's still some average. And hopefully from one group to the next, that average didn't jump around too much. Even if the distribution didn't match the shape I wanted, if I'm simply graphing that common value for every single one, there should be some pattern with that common value where it is stacking up kind of similarly. In fact, there is. So we have some prerequisites to look at. Sometimes for when we're talking about averages, actually like X bar, if we already had individual values that were bell-shaped, well, Merry Christmas, you will continue to have bell shapes on your grouped values, on your sampling distribution for X bar. If X bar did not already have a normal distribution, you may have heard me say a second ago, you would need a sample size that's sufficiently big, right? And the bigger the sample size gets, the more beautiful this picture will get. The more consistency will start to come out, and the more you're going to see the true pattern. It starts to get skinnier and skinnier, more consistent these pictures do. But the idea is that we do approach a normal distribution. Might take a little while, depending on the type of samples we're collecting, what those shapes are. But eventually it will happen. A lot of statisticians use 30 as a rule of thumb. That's not always the perfect number. We'll talk about that as we proceed through chapter 17 and future chapters. We sometimes need a larger sample size. Larger sample sizes are typically considered better, no matter what, whether it started off normal or it didn't. We like to have good, solid samples. But the idea here is that we are approaching conversations about things like the central limit theorem. The power of taking individual values and thinking of them now in smaller sample groups or in bigger sample groups, whatever. You're talking about samples. And it's a theoretical thing. You don't actually go down and take tons and tons and tons of different groups of size 50 and graph them. You actually get one. And you say, if I'm looking at the average, I know the behavior I expect as long as I qualify with this criteria, right? So it's a conceptual thing. I guess if you wanted to torture yourself, you could, because we know one of the prerequisites is that this stuff needs to be repeatable. Any sampling that we're doing to come up with a statistical inference, or even just to analyze what the data is doing before making an inference, needs to be repeatable. But what other features do we need? So actually for part 1, Sampling Distribution Models Part 1, we first begin with proportions. I know I started the discussion with X bar because I like to think about that one first. But we have a similar thing going on. Now it's not the exact same thing because there's actually an extra bridge to cross over whenever we are talking about percentages. So let's get to that bridge. Let's talk about that. And then we'll get into the main core of the lesson that will match your class notes. You see, with proportions, you may remember that we typically have something called P, which is the probability of success. Actually, I'm not sure that you would remember a lot about that. Well, I'll talk to you more about it in a second. And we have something called Q, which is the probability of failure. mean, I know you've seen things like p hat before in your summary statistics. We may have talked about q-sum. I don't remember right off right now. But the idea is with proportions, we tend to treat proportions as things that have two outcomes. It's not always going to, there's other types of grouped up data we can look at later, but for this discussion right now, I'm talking about binomial. I'm talking about distributions that only have, and have exactly, by two outcomes. Yes, no. Success, failure. Right? Whatever the outcomes might be, there's just two of them. Okay? And in looking at the two, we typically will deem one of them success, one of them failure, so we can talk about the probability of something happening. So for example, I might say I'm going to look at people wearing seatbelts versus not wearing seatbelts, right? What's the probability that someone is wearing a seatbelt? That's going to be my P, right? Q will be equal to 1 subtract P. So the probability of Q is always the complement, the exact opposite of the probability of something occurring, because literally you just have the two different outcomes. So complement rule kicks in right there. And I'm using just a regular P and Q here. You may remember from our notation that when you see that, a lot of times you would have thought of that as being for the population, right? So on a smaller scale, we might actually use P hat, Q hat to talk about sample numbers. What was that sample percent that we saw in our data? And in its origin, if you go play in StatCrunch, for example, now binomial actually comes from taking something called the Bernoulli distribution, which the Bernoulli is when you're just saying in general what's the percent of yes as the outcome and the percent of no as the outcome, and we've counted yeses and nos, right? The binomial takes a step further and starts to say, okay, well, if I know I'm going to repeat something several times, and I know the probability from that Bernoulli of it being a yes or a no, can I figure out the probability of something happening? Okay. So there's two kind of similar, in my mind, they kind of go together as BFFs, distributions. One starts off originally just talking about, let me go back to this. One starts off just talking about the outcomes. And how often they happen, right? What percent of the time? So you took your data, you saw the balance of it, you see the yeses and the nos, right? And then binomial takes it a step further, and it starts saying, okay, well, I'm going to repeat the same thing a few times. I'm going to have n trials. And knowing this behavior from the Bernoulli over here on the left, if I repeat the same thing a few times, what kind of a balance do I expect? How often am I going to expect to get this many yeses or this many nos? Let's quantify it differently. So this distribution you're looking at here, for example, here's an n equals 10, and I gave you on the little thing I sketched, I put 60% for probability of success. Maybe I would say, you know what, I want to look at this picture where X is the number of successes for 10 trials, and I just now said down here, what's the probability of me getting 5 or less successes on whatever I'm talking about given this information. So it takes Bernoulli to the next step where you're now making something kind of reiterative. It's happening again and again and again, and you're looking at the likelihood of things piling up in certain ways. Now what I want you to notice is that the binomial is a discrete, separated bars, discrete distribution initially. In fact, it actually always is, technically, right? So let me write that. The binomial which takes Bernoulli and adds some trials and starts to talk about now number of successes. It's counting the number of successes here. It also, just like Bernoulli, It is discrete, separate, not continuous. So you start getting counts, number of yeses, and you get literally, you know, there's 0, there's 1, there's 2, whatever the shape might be, right? Where this over here is still your frequency. So that's like the early on journey between Bernoulli to binomial. In this sampling distribution section, we go one more level, one more step. We say, well, wouldn't it be nice if I could take the binomial distribution and I could think about it like it were normal? Can I treat a binomial normal? Can I treat it like it is a continuous variable? Can I know if it is a normal shape, or say that I would expect there to be a normal shape? Because I sure would like to get back to this point, just like over there with the X bar on the first slide we looked at together, or first portion of our notes. I sure would like to get to a point where I can think about it like this. Even though I know in theory that 0, 1, 2 up here on this original picture, that they are discrete, they are separate, can I get to a place where I can just think about it in a fluid way and know that I have a shape that I like and be able to talk about probabilities in this nice way off that normal distribution? And the answer is absolutely. We do have some conditions to meet. One of the most popular conditions, one of the initial ones that you definitely want to be sure of, is that n times p and n times q need to be bigger than or equal to 10 in order to even get a normally shaped distribution. And you can go on your computer and try different p's and different n's and start watching that shape change, because it will. Our initial one, I think, started off already looking kind of normal, which, let's see, we weren't guaranteed that it would be normal with such a small sample size of 10 trials. But it would get more normal if I increased the sample size like this. Watch. Ooh, look at that. That's way prettier. Let's make it 1,000. Oh, look at that. These are nice, right? Sometimes they start off relatively normal like we already saw, right? But we're just not guaranteed that we can treat it a binomial as if it's normal unless we meet some criteria. That's what I'm trying to say here. And so the criteria is when we are looking at overall summaries, we are looking at p hat. Instead of looking at stacks of X bar for the sampling distribution when we're dealing with sampling distribution for the mean, sampling distribution for the proportion is doing something similar where you're saying I have this entire group, this is my sample size, what was the percent that I observed? Let's see how frequent it happened. Let's talk about this in normal terms. And this in subtract, or n multiplied by p, n multiplied by q, both of them being greater than or equal to 10 to qualify. And we actually think about this a lot of times using the sample data, we'll test it, right? Or if we have some pre-thought of idea from a previous study, we'll test that information also. But in addition to that, we do have some other prerequisites. But that's the conceptual build for what we're about to learn.